Hello, grade 12s. It is good afternoon the side, so good afternoon or good evening from for you guys. In this session, we're going to be working more in particular with electric circuits and more especially on the internal resistance type of questions. But essentially, we cannot deal with the grade 12 part of the electric circuits without getting into the grade 11 part first, because really we have to start fixing from those sides first. So we're going to work on the grade 11 side first. So the grade 11 side was just basic electric circuits. Okay, so what we recall on electric circuits was the fact that we had two kinds of electric circuits. Now I'm sorry to go into such dumb stuff, going all the way to basics, but it is necessary. So what we recall is that we had two types of electric circuits. We had series circuits and we had parallel circuits. Okay. What we recall is that in a series circuit, there's going to be one branch of current. So what we essentially mean is you can have a kind of a circuit that looks something like this. Okay, and then maybe you have a light bulb there, and that's it. So essentially what this looks like is you just have one branch of current like that up until it is done. It's like that. And then we had a parallel circuit, and the parallel circuit had um, multiple branches. Okay, it had multiple branches. Now what this essentially meant is that we would have our current divide itself into two or more pathways. So for instance, you can have an arbitrary circuit like so. Okay, and then it can branch into two like that, and you can have one light bulb there, and you can have one light bulb there, and then it closes like so. Okay, and then what we then discovered were quite the differences between the two, and we had to really keep this in mind, especially when we get those kind of questions where they would give us series and parallel combination, where you'd have one circuit that has both types of circuits. Okay, so you'd have to know those properties and what would keep them different, and as well as some of the formulas that you can denote to use depending on the kind of question they give you. So let's start off with the resistance in a series circuit. So resistance in a series circuit. In a series circuit, we calculated our total resistance in the series combination. Keep this in mind. We calculated this just by adding, because it's just R1 plus R2 plus R3 and thy kingdom come. And then in parallel circuits, the resistance in parallel circuits was calculated differently, and this is the part where I usually have my students use the best formula that works for them. So the formula that was given was the 1 over r parallel formula. The one that will say 1 over r parallel is 1 over r1 plus 1 over r2 plus blah blah blah. Now the issue with this formula that I have is the fact that you have to flip your fraction afterwards, and then simplify your answer from there. So you'd have to flip both sides, meaning you would simplify this side, and then once you're done, you have to flip the fraction so you can actually get to the r parallel. And I have an issue with that because of the issue of time. So I would prefer using the formula r parallel is equal to 1 over r1 plus 1 over r2 plus 1 over r3. You're probably like, Nash, come on, man. What are you doing, man? Oh, come on. This is the change that we're going to do. We're going to put in a beautiful -1 just so that it actually does the whole flipping of the fraction automatically. So meaning if you put it in the calculator, you're just going to put it in like that, and then you're done. You don't need to flip fractions afterwards. Okay, this was one of the two differences between the two second types. Then we had to know that they differ through these aspects. If you check the Mindset Extra document, it has a whole table of these differences, but the part that we're going to mainly focus on is these two. But I'm just going to highlight the parts that we really need for now. So working with the series circuit or the series combination, what was different is that in a series circuit, current is the same. Okay, that is the worst handwriting in the book. Okay, let me just do that. Let's clear that out. Okay, current is the same all across all those series components. So what I really mean is, if I have a, let's say I have a series circuit like so, and I have a resistor here and maybe another resistor there, and then I don't know, maybe another resistor there, and so on. So if I have this like so, what they really mean is the current across this resistor would be the same as the current across this resistor and the current across this resistor. Okay, so that is essentially what they mean by that point, is that as long as they are in series with one another, then the current is the same. Now I want you to also denote this as well, is that even if you have series and parallel combination, you can also denote that whole thing that we have there. So let's suppose I have a resistor here, okay, and this resistor is in series, note, with a parallel circuit of other resistors as well, like this, and I'm sure you've seen many of these. If we have this kind of a situation here, we can still have this point being valid. What we're saying is the current in this entire thing here, okay, this entire parallel circuit, the current that we have here shall be the same as the current in just this. Reason being because they are, well, they're in series with one another. As you can see, the series, the resistor here is in series with that parallel combination that you have there. And then when it comes to the parallel circuit, one thing we have to then keep in mind is the fact that potential difference is the same. Okay, potential difference is the same. What I'm really meaning is, those who don't know what potential difference is, it's voltage. Okay, what we're saying is just that it is the same. So what we really mean is the fact that oh yes, in a parallel combination, potential difference is the same. I had myself in a snag there. So here, if we have this battery that is supplying power, or rather voltage, into a circuit, and then that circuit has a parallel combination of these resistors here, like so. Okay, what we really mean is, if we look at this quite intensively, actually I drew this, actually I should have a short one there. Yes, so the current will go in there, remember, from the long side. It will go in and then it will divide. Okay, the current will divide, not the potential difference. Okay, the current will divide, but now the potential difference is pretty much the same. So let's imagine that this gave in 6 volts. Okay, so what we're really essentially saying is that 3 volts would be there and 3 volts would be there. We're just gonna have the same stuff. Okay, they have to be equal, they have to be the same on all combinations of those parallel circuits, on all branches. That is essentially what we are saying. Okay, so just keep that in mind. Then if you go through this document, there were these formulas that we were given. Okay, but firstly, there is a thing you have to remember out of the grade 11, which was the special Ohm's law. Okay, so Ohm's law is the one that I like telling my students is called VIR. Okay, it's called VIR, and what this is that for special formula that says V is equal to IR. Okay, so you have to know that the the definition of Ohm's law says the potential difference across a resistor is equal to the it's actually inversely proportional to the resistance and directly proportional to the current. So you have to know that definition. There's no way around it, and you make sure that you do know it according to the guideline that you were supplied. Then once you have encapsulated that, then you have to be able to see the proportions for that. So if you've been quite a student of mine for a while, you'll know that we don't really cram proportions. You just need to put it in the form of a fraction, and then from there you'll be good. So here, this right now there is no fraction. Okay, so we can make either I or R the subject of the formula. Let's suppose we choose I to be the subject of the formula. This would mean that we'll divide both sides by R. So this means that we're going to get V over R is equal to I over R. So what we essentially did is we just divided both sides by R. Okay, just divide there by R and divide there by R, and it will look like this. Then essentially you will see that the R's there will then cancel, and then you're left with I is essentially equal to V over R, which is another mutation of this formula that you were given in grade 11. What I like is when it looks like this, I can actually see the proportions. If you remember what we said, for those that I've taught before with the Doppler effect and all the other formulas, is that the numerator is always a direct proportion, okay, and the denominator is an inverse proportion, okay, like so. It's an inverse proportion. So what we can then denote is that V is directly proportional to I, but it's inversely proportional to R. Easy as pie. It is easy. And we can actually test this out. If you have something like 10 over 5, well, 10 over 5 is 2, because that's just 10 divided by 5, it's 2. Then remember what direct proportion means. Direct proportion means if I increase one of them by a specific factor, the other one should automatically do the same by the very same factor. Meaning if I double, for instance, the V, the I should also double, like so. Okay, so let's look at this fraction, for instance. If I double this, what would happen to the 2? So if I double that, I would get a 20 over 5. Okay, so the 10 has actually has essentially doubled. Then what happens to the 2? Well, the 2, well, 20 over 5 would become 4. You would see that this has also doubled. That's what we really mean by a direct proportion. Then you're like, okay, what about the inverse one? Well, the inverse would mean that if you increase one by a specific factor, the other one would do the opposite. It would decrease by the very same factor. Okay, so let's suppose we double this one, and let's see what happens to this. So 20 over, instead of it being 5, we're going to double it and make it a 10. Okay, then it would change from 4 to actually a 2, because 20 divided by 10 is a 2. So you'd notice that that one also then does the inverse by the very same factor. So same thing happens if we have formulas in that form. Okay, so what we can then note is that if we were to double the potential difference or the voltage, then the current would also double, but the resistance that we're then going to get would be half, like so. If we multiplied by 3, then the other one would divide by 3, and those that are indirect would multiply by 3 as well. You get the draw. Okay, and remember the difference in your graphs. Okay, remember this is a direct proportion. Okay, and then there's this argument here. You can have graphs that do this, or you can have those that do this. Okay, so question is, which one is the inverse proportion? Is it this one or is it this one? Well, the one that is a inverse proportion is this one. Then you're probably like, well, what about this one? Well, remember we said it has to decrease by the very same factor. Okay, this one you'll find that the decrease that you have from here to getting here is not the same as the decrease you would have from here to getting here. So this is not the same factor, but this one is the same factor because essentially the gradient is the same everywhere. Do you see that the decrease you would have everywhere is exactly the same? So then that would be your inverse proportion. So those would be the two kinds that you are going to then have. Okay, so with those in mind, we can then explicitly then push into the grade 12 content. Okay, but before we then do that, let's get the backstory here. Let's get the backstory. Okay, what is the story in the grade 12 electric circuits. Well, the story now is the whole concept of internal resistance. Okay, so idealistically speaking, if I'm to buy a battery, an arbitrary battery, and suppose this battery has a reading of maybe 12 volts, the fact that it has a reading of 12 volts, it just means that the maximum that it can supply into a circuit is 12 volts. But this is all theoretical. Okay, this is all in theory. But if you look at this battery quite closely, you'd realize that inside this battery, if we really look at it quite intensively and closely, you'll notice that you've got these electrons that need to be pushed out. Okay, but in there we've got all these chemicals and all this this wara nyara nyara inside it, and all of this is really slowing down these electrons from being pushed out of the circuit into the main circuit itself. And that is internal resistance. That is the idea behind internal resistance. So you'll actually figure out that the fact that we have the battery having the writing of 12 volts on it, but if we really put in a voltmeter around it, we're not going to get a reading of 12. We're going to probably get a reading of like 11.5 or something like that. And that is the theory of what happens with internal resistance. So essentially, the reading that we actually have on that battery is what we know as EMF. Okay, that is the whole idea behind EMF. And EMF, like so, to really get the idea of EMF, it's that we're taking the voltage of the external circuit and we're just adding the voltage of the internal circuit. And the voltage of the internal circuit, we're just talking about the one that has been lost. Okay, the one that we're not really counting, the one that has, that has been stopped by those chemicals and the wara nyara nyaras inside the battery. Okay, so that is essentially the idea behind that. So just keep this whole idea in mind. So then let's try to extrapolate this formula. What do we know about voltage out of Ohm's law? Well, we know that V is equal to IR out of Ohm's law, right? We did Ohm's law just now, so you should be quite fresh with this. So it's equal to IR. So then we're going to get quite xenophobic and really segregate these things. Okay, so what we do know is, let's suppose we take a circuit. Okay, now I'm going to put in the whole idea of internal resistance into consideration here. So let's suppose that's our internal circuit. Okay, that's just representing the battery, and then we have the whole circuit stuff, and maybe we have some resistors and maybe some emitters and so on. But now this battery here has its own resistance and its own voltage. Okay, and it has a current as well. But what you realize is that this battery is actually in series with the outer circuit itself. Okay, so I'm going to give it an IR. Okay, because yes, V is equal to IR plus, and then the internal is also a V is equal to IR. But what they're really now doing in Great Off is they are now making those R's different. They're making it a small r. Then now you're probably like, well, Nash, are you saying that the currents, they are the same? Well, yes, the currents are the same, because remember now that the battery is connected in series with the inner with the external circuit actually. So then we kept in mind that current in series is equal, it is the same, it's constant. So the current in the battery is going to be the same as the current that is actually in the outer circuit itself. Okay, so then this formula then will then suffice. So then we can even factor out the I and have it as R plus R. Okay, and remember, R is external and the small r is internal. Okay, and this is really a formula that we are going to be using quite a lot. Okay, so let's practice this a bit. Okay, let's suppose we have a circuit. Okay, so I'm going to have an internal circuit. Just remember that if they show you some dotted thing like this, okay, that is essentially just showing you that it's an internal circuit. It's just the circuit of the battery having its own resistance and its own potential difference. Okay, just keep that in mind. So now we have this battery. Okay, and then I'll probably do something like this. okay, something like that. So you'll have it like this, and then we're going to connect a voltmeter like so. We're gonna connect a voltmeter, and then we'll just work on the outer circuit. So maybe somewhere around here we're going to connect, okay, maybe that's the worst way to introduce that. Okay, I'm just gonna put in a resistor of maybe 2 ohms, a 2 ohm resistor, and then we're going to the other circuit, and then we're going to put in a emitter. Maybe that would be a1, and then we're going to have maybe another resistor of 3 ohms, okay, for instance, and then we're going to have, let's maybe even add a parallel combination here. Okay, we're going to work on a parallel combination. We'll put in a parallel circuit there, okay, and then we'll close that off like so. Okay, now let's suppose the EMF that we really have here is let's say maybe 10 volts. Okay, and then we're going to have an internal resistance of, so the internal resistance they can give you around the whole thing, or you'll essentially see that they can have a resistor there. So I'm going to give this resistor maybe a 1 ohm. Okay, and then these ones I can give maybe a 1 ohm and a maybe a 4 ohms there. Okay, and that one is 3 ohms. Okay, then out of this, let's calculate a1. Okay, let's find out how much is a1. Okay, a1 is really essentially that one. So how do we do this? Well, we can use our formula. So what we do know is the fact that current, remember a1 calculates, it measures current. So what we do know is the current across this thing is going to be the same as the current across this, and the same as the current across this, and the same as the current across that. So where do I have more stuff? Well, I have more stuff in the internal circuit. That's where I've got more stuff. Okay, because here essentially I don't have the potential difference there. Okay, but I have more stuff in this one. Okay, and we do have the formula to work inside that internal circuit. So inside the internal circuit, we recall that we can use the formula E is equal to I, and then we have R plus R. Okay, we recall this, we remember this, we all cool, and we have all this stuff. Do we have the E? Well, we do have the E. It's 10 volts, so I'm gonna put in the 10. Okay, and then the current, do we have the current? Well, no, we don't have the current. That's actually what we're looking for. And then the R, remember this capital R is the external resistance, so meaning we're going to sum up all the resistance in the external circuit. Okay, meaning we're going to sum up this, and we're going to sum up that, and we're going to sum up that and that. Okay, so let's work on this on the side. So this is what we have. We've got a, let's work with the resistance in parallel here. Okay, so we're gonna work on the R parallel first. So we recall the formula that I best like. Remember, you can use the 1 over R1, the 1 over R parallel formula, but I'd prefer this one just for the sake of time. So 1 over R1 plus 1 over R2. Now I'm not going to write down the formula, of course. I mean, you guys know this. So I'm just going to say 1 over 4 plus the 1 over 1. Okay, this is the 1 over 4 and the 1 over 1. Remember, they're in parallel. That's why I'm using this formula. And then I'm going to close this out and put it to the power of negative 1. Okay, and then we're going to sum this up. So here we're just gonna use the calculator, guys. Come on. So I'm just gonna hook up the calculator. Calc. So Uncle Calculator is gonna come out. So we're just gonna punch that in as it is. So we've got a 1 over 4. Okay, plus 1 over 1 is just 1, so I'm just gonna put it in as it is. Okay, so this is what we essentially got. Okay, 1,25. Now, oh, okay, well, this is the worst calculator. It doesn't have fractions. Let's just work this manually. So we're gonna have 1 plus 4 over 4. Okay, I just found the lowest common denominator there, and then we're going to have a 5 over 4. Okay, and then 5 over 4, we still have the negative 1 outside. We haven't used the negative 1 as of yet. Okay, Now you guys probably use Casio calculators and you probably fasted this. So then we have a 5 over 4, which is just going to be the same as the 4 over 5 because of the negative 1 that I have there. Now remember, you guys did it with the calculator, you probably had the answer already. Sorry for that. So then essentially what I'm then going to do is do the 5 divided by the 4, and then we're going to get 0.8, like so. And remember, this is 0.8 ohms, so which means here out of this whole parallel circuit I'm going to get 0.8 ohms, and then this should be added to the 3 and the 2. Okay, so meaning the R total is supposed to be the total of the series plus the total of the parallel, where we actually calculated the total of the parallel. Then the one for the series, remember the series, we just have the 3 plus the 2. Okay, so I'm just gonna do the 3 plus the 2, okay, plus the parallel I got a 0.8. okay, then I'm just essentially gonna add all this together. So I've got 3 plus the 2 plus the 0.8. okay, we add that together and we get a total resistance of 5. Was that 5.8? Yes, 5.8. okay, so that is 5.8 ohms. So meaning for that R I'm going to get a 5.8. This, remember, that was the external, and then for the internal, remember the internal is given as the small r, the resistance in the internal circuit, so that is just 1. okay, so then we do the math. I'm just going to divide both sides by 5.8 plus 1 and divide there as well by 5.8 plus 1. okay, then essentially what we're then going to do there is just let the calculator do the work. So I'm just dividing 10, so this is just 10 divided by 5.8 plus 1. and I'm just going to close that bracket and get my 1.47. so then my current is 1.47, and remember this is amps because this is current that we were calculating. Okay, pretty easy. Then let's calculate the V, that voltmeter reading. Okay, so question is, what is that V really measuring? What is the V the voltmeter, what is it measuring? Well, this voltmeter is connected to either ends of the battery, so meaning it's actually calculating the total voltage out of the external circuit. Okay, it's calculating the total voltage out of the external circuit. So now you're like, well, Nash, how do we do that? Well, we can use Ohm's law. That's one thing. We know that V is equal to IR, but now we're gonna have to segregate things here, because remember that V is calculating for the external circuit. So if I'm using this, I'm gonna have to put in a current for the external and a resistance for the external. Okay, we have to segregate. We have to be quite xenophobic here. We cannot use people from the foreign land to work for us. Okay, so what we know about the current is that it's the same. We actually have the current before, so that's the 1.47 that we had earlier, so that's just 1.47 there. Okay, and then for the resistance, or the resistance, remember now this is the external circuit, meaning I have to sum up everything out of the external circuit. Now for the sake of time, we actually did this before. We got that 5.8 before. Remember, that was the external circuit, that was the 5.8. That's the internal circuit, guys. And there we go. The external circuit there we had was 5.8. Okay, so we do the math, and we use our calculator. Okay, so let me just do the 1.47 multiplied by 5.8. okay, and then we get 8.53 basically. Yes, 8.53. and remember this is volts, so remember your units as well. Okay, so easy as pie. Okay, now I've got another question written down. Okay, let's do another one. Okay, let's do another one. So let's suppose I've got a circuit. Okay, I've got a circuit, and in this circuit we've got a battery. an internal circuit rather. We've got a battery, and inside this battery we've got its internal resistance of 2 ohms, and then you have, you know, the power supply. You guys, you know the drill. You've got the power supply itself. So remember, they'll draw this with a dotted boundary like that. I'm just drawing it with a solid line. I don't know why, I'm probably stubborn. So we do it like so, like that, and we put in the resistor there, and then we're going to have a parallel combination there. Okay, we'll put in a parallel combination, and like so, and then we're gonna have 10 ohms there. We'll call this P, and then we're going to have another one here, and we're gonna call this the 15 ohms, and we're gonna call this R, and then that is it for the parallel. Okay, and then we'll make this then go around and maybe have an ammeter there. Okay, and then this one is measured, this one is Q, and is measured to be 10 ohms. Okay, and then this is hooked up on a voltmeter. Okay, like so. Okay, so now we have everything that we need. Then the questions there are, number one, they want you to determine the reading on the ammeter. Remember, the ammeter is right there. They want us to determine the reading on the ammeter. And number two, they want us to determine the reading on the voltmeter. Okay, they want us to determine the reading on the voltmeter. Sorry. So now let's start with the ammeter reading. Okay, what we do know about the ammeter reading, just like the previous question, remember that you have to be able to see what is in series and what is not in series. We can see that this is in series, and this is in series, even with the ammeter itself, and this is in series as well. So where do we have more stuff? Well, we have more stuff in here. Okay, we have more stuff in there. Let me see if I missed anything there. Let me see that. No, I did not miss anything for that. Okay, so we probably have more stuff in here, but question now is, oh, we're not given the I'm not sure if I wrote that or I didn't write that. Okay, no, I didn't write that. I did not write that formula. Okay, well, that's fine. Okay, that's fine. Let's work in the external circuit then, because we have no stuff, we have less stuff in there. So we can use Ohm's law. So I is V external over the R external. Remember, this came out of the same formula as V is equal to IR, but remember, we did the whole situation of just segregating things. Okay, we just segregated stuff, we just divided stuff the way we felt necessary. So, okay, oh, no, I'm using the wrong formula here, am I? Yeah, I'm using the wrong formula here. This would calculate the current. No, let me just erase that out. Yes, we're calculating the current, sorry. So to calculate that current, we're going to use the we can use the internal circuit. Yes, so we know that I is E is equals to that IRR. Okay, then we are essentially looking for this, because remember, the ammeter measures the current essentially. Okay, and then we have this, isn't it? We have all those. Okay, then we were not given that. Oh, I did not write down that current. Oh yes, this is 6 volts. Yes, it is. Oh yes, I forgot to write that down. It's 6 volts. So now that we know the reading is 6 volts there, meaning our EMF is 6 volts. Okay, so we've got 6 volts there. Okay, then we are looking for the current essentially. Okay, we're looking for the current. Then for the resistance, remember the R is for the external resistance, so we're just gonna sum up all these guys here. Okay, so first things first, I like taking preference of the parallel circuit, so we're going to calculate the R parallel first. So the R parallel, so back to the formula that we did, so 1 over 10 plus 1 over 15, essentially like so, and then to the power of -1. Okay, and then we're going to do the math there. So I'm just gonna do the whole lowest common denominator thing. So we're just gonna get 15 plus 10 divided by what is 10 multiplied by 15? 150. I don't know. Yes, 150. Okay, I'm just using the lowest common denominator. Then that should give us 25 over 150, if my math suffices. Yes. Then we're going to do the math there, and remember we still have the negative 1 outside. Okay, so 25 divided by 150, so I'm just gonna do that there for you to see. So we're going to have in fact, what we're going to just punching in the calculator is 150 divided by 25. You guys probably did it in the calculator already and have the answer, but anyways, we get 6 for that. Okay, for the resistance there. So what we then did there was 150 divided by that. Yes, so we get 6 ohms. Okay, and then we're going to sum this up with the series circuit, because remember, your R total is going to be your R series plus the R parallel. Order does not matter in that case. Okay, so what do we have in the series? Well, in the series we just have the 10, okay, plus, and then in the parallel it's what we just did now, which was the 6. So essentially we're going to have 16 ohms. Okay, so that's how much we have in the external circuit. So that's 16 ohms plus, and the internal circuit, this is given right there to be 2. Okay, and then I don't know why I wrote the ohms there, sheesh. Okay, then let's just simplify that. So I is then 16 plus 2, and 16 plus 2 is 18. Okay, and then we do the math using our sidekick, the calculator. So to of course simplify the current, we're gonna divide both sides by 18. So we're just gonna have 6 divided by 18, and then we just sum that up. We get 0.3 ohms. So I is then going to be 0.3 ohms. Okay, so that means we've got 0.3 ohms of current here, and going to be the very same 0.3 ohms of current there, and 0.3 ohms of current in the parallel combination that we have there. Okay, so of course it is 0.33 because you have to round off to the nearest 2 decimal units, of course. Then now let's calculate the V, which is that one. Remember, the V it actually calculates the external voltage. Okay, so we can use Ohm's law for that. So I, okay, let's actually start from the beginning for that one. Okay, V is equal to I R. Okay, then we're going to sum this up and put it in the best way possible. So then I is actually equal to V over R. Remember that we're going to segregate things, so meaning we're going to use external everything. Okay, because we are essentially trying to find external stuff basically. Okay, so everything is external. So let's look at the current that we have. For this guy, we actually calculated the current, and remember, current is the same everywhere. So the current we actually calculated was the 0.33. So 0.33. Okay, and we're looking for V. So I don't know what the V external is. Okay, do I know the external resistance? Well, yes, I actually summed up the whole external resistance. This was the V total that we're doing there, and that was 16. So I'm gonna put it in there. Then to simplify and leave the V external alone, I'm gonna multiply both sides by 16. So we'd have the 0.33 being multiplied by 16 essentially there. So we're gonna get a 5.3. So meaning the V external is going to be, what was the answer there? Well, that was 5.3. 5.3, and remember this is volts. Okay, so you guys are gonna go ahead and of course practice these internal resistance questions a little more and more and more and more, and keep practicing them. And then please remember, of course, if you have questions, you can leave them in the chat box in this premiere video, and then I'm of course watching with you guys. I had to make this, of course, a premiere because I am not at home right now. I'm actually in Harvard right now, and we've been working on these training workshops for a while now, so I'm just working on my teaching skills more and more. So you guys, of course, keep practicing these guys more and more. So in somewhere attached there will be a link to some of the resources that we have here, the notes, and also some practice questions as well, together with their memorandums. And of course, remember guys, if you probably have my WhatsApp. You can inbox me if you face any questions. Moving on, if you may face any of those questions, I'll be glad to respond. Now, probably around this time, I may not respond on time because I may be occupied, but I will be sure to, of course, respond at some point in time. So, good night, guys, and remember to keep practicing those and do not bear that sword in vain. I'll see you guys in probably one of the next lectures in the future. See you.